All right, good afternoon, everybody, and welcome to today's special RAL M-Cube seminar. And I'm very pleased to introduce our speaker today, Dr. Zhang, who is with the Water Cycle Applications Program in RAL as a scientist for, and very thankful he's here to present on all the exciting research he's been working on here at NCAR. Just a little bit of background. He works in regional climate modeling and land surface processes and shallow groundwater simulation. He's done some work in the prairie pothole region in collaboration with Ducks Unlimited Canada, by the way, and also does work in integrated land surface crop irrigation modeling and looks at the impacts of precipitation from land surface processes and quite a bit more in the related fields. Going back in time, Zhang received his Bachelor's of Science at Lanzhou University in China in 2016. And during that time, he was an exchange student at the Department of Meteorology at the University of Reading. And then after that, he came to Saskatchewan, the University of Saskatchewan in Canada and finished there with a PhD in 2021. And that was in the School of Environment and Sustainability, Global Institute for Water Security. So during this time, he was often visiting here at RAL under Fei Chen, Michael Barlage, and Changhai Liu. And that later led to an ASP postdoctoral fellowship here at RAL, and luckily we still have him here today. In his free time, I've realized he's a runner and hopefully enjoying the great weather that we're having. So I'll turn this over to our speaker now.
Hello, hi everyone. Thank you, Chris, for the warm introduction, and thank you everyone for showing up to today's presentation. So as Chris introduced, so I came from the regional climate downscaling world, and then the NoahMP land surface model coupled with WRF. So, and then right now I'm working, this work is mostly related to the NoahMP coupling with MPAS, and then the capability to do S2S predictions. So as you can see, this is a very broad and collaborative team effort. So the scientists from, it's a cross-lab collaboration with scientists from RAL, Cenling, and I am the NoahMP land surface model group, Shanghai, and then also scientists from NQ, Judith, Abby, Julia, and then scientists from CGD, Kai, Yaga, and Meg. Also Sebastian, he's also a scientist in EOL. So to start with, this work is supported by the NCAR initiative for Earth system prediction across timescale. At the first phase, we started to look into the subseasonal-to-seasonal forecast, and then with a specific focus on land atmosphere interactions. So, okay, let me find the pointer too. Yeah, this work is, we have two big parts. The first part is, our part sits in the MPAS and NoahMP couplings on the left-hand side. So Abby and Judith help set up the MPAS S2S prediction suite. And then we in Cenling are looking at this NoahMP coupling in the MPAS. On the right is our colleague from CGD working on CSM, same problem S2S prediction, but looking in the CSM. And Meg and Sasha are looking in this field. And also we try to leverage as much as possible the Earth system prediction working group in CSM. This is also a cross-agency collaboration between NOAA, NASA, and DOE. We had a cross-agency workshop back in June in Mesa Lab. And then there's open working group in the community back in April. Just to show you some of the activities we've done. So this year in June, we had this cross-agency, multi-agency community workshop focusing on land atmosphere interaction in S2S predictions. So we have scientists from NCAR, NOAA, NASA, and DOE that we try and join together to look into the source of S2S predictability with land surface model initialization, diagnostic, and then what are the skills, and trying to design coordinated simulation together. Another exciting activity came from this August in UT Austin. So we had this NoahMP international workshop, but also it's framed together as a joint effort of UT Austin and UCAR with looking to the land model resilience for Gulf Coast region. We had a really nice turnout in 260 attendees and then 75 in person, over 180 virtually. You can see that NCAR scientists, particularly from RAL and CGD, has a really nice turnout. Many of the scientists were wearing blue shirts accidentally, but Mike was wearing a white Hawaiian shirt. So today's presentation, I'm trying to give a broad sense of what are the motivation, what are the introduction of what we are doing. When we're trying to look into one long-term simulation with MPAS coupled NoahMP, we look into the global temperature, precipitation, winter storm track, tropical variability. And then from the land atmosphere interaction perspective, we want to look into some of the snowpack issue, soil moisture, latent heat flux coupling. Those are the first part of today's talk. And on the right-hand side, we're going to focus on the second part, which are, we already built up this long-term simulation. Can we use it as a baseline and then to build a S2S prediction suite and look into some of the extreme event that happens very recently. And then we will look into some of the future steps. So I have to acknowledge this is a really broad range of topics, so I might just give a very broad overview of some of the topics and then pointing out some of the potential issues we've seen and then what are the potential room for improvement and look into the future. So many of the results are already submitted to a preprint for JGR Hemisphere this July. And thank you. If you are interested, feel free to check out this online. Okay, so what are these S2S prediction? Why is this important? So in terms of predictability, that usually when you're at the deterministic forecast range, usually shorter than 10 days or 14 days, the predictability it actually looks okay. So it decays with your lead time. And then to the long end, you see that the predictability over a seasonal timescale is also fairly okay. But what sits between is this subseasonal timescale, and it is often termed as a predictability desert. So Yaga and Everett had a US paper out just recently saying that we need to join force to solve this forecast predictability desert. So what can we do for this front? There has been hypothesizing by Portemore, this is the figure he put together, is that for the time period between day 7 to day 30s, have the land actually can contribute most of the predictability over atmosphere initialization on oceans. So the hypothesis is that if we can correctly initialize land surface and then representing the land atmosphere coupling right, that potentially improve our subseasonal predictability. What are these land atmosphere coupling process we try to look into? So one simple index that we're trying to look at is this terrestrial coupling index. So it's calculating based on two variables, latent heat fluxes and then the soil moisture. So basically taking the standard deviation of your latent heat fluxes and then times the correlation between these two variables. So it tells you that how these two variables are correlated and what are the magnitude of your soil moisture can change your latent heat fluxes. So we're going to look into this from one of the long-term simulation we're going to look. Okay, this is our MPAS model set up. So you might ask, if you want to do subseasonal forecast, why do you need a long-term simulation? The reasons are multiple, because first, we want to build and establish a model long-term performance. It's really that this short-term deterministic forecast biases will resemble long-term biases. Instead of doing it repeatedly with initialized forecast, if you do a long run and then you can diagnostic the model performance, then it will really help you to improve your short-term deterministic biases. And for the S2S forecast, people usually look into not the raw temperature versus observation, but then you need to remove a climatology and then evaluate it on the anomaly space. For many of the land atmosphere coupling strength indexes that are also evaluated over a long-term period. And then we try to demonstrate a model capability for S2S prediction. So the study, the simulation we conduct is from a 25 years long-term simulation at global 60 kilometers. So right now, this is not convection permitting to some degree. We're using mesoscale reference suite, and then using one initialization of ERA5, and then with daily prescribed updating SST and then CIs. So, and then with time varying greenhouse gas, and then the version we use is 8.2.3, and then with the mesoscale reference suite, just changing the land surface model from NOAA to NOAH-MP. So to frame it, like it's more of an AMIP style of simulation that you prescribing the SST and then looking to the atmosphere response. So what are the model performance? So just to give you a quick sense, so we're right now, most of them are looking into the global annual mean biases. And then as you can see, the top figure is the biases between model performance over ERA5. And then the bottom figure are for the zonal mean. It is very obvious that the biggest temperature biases occur in the high latitude ocean region. What happens there is, and you also can look into the seasonality patterns. You can see that these cold temperature biases over a high latitude ocean will shift from season to season. In MAM and JJA, it's in the summer hemisphere, it's in southern hemisphere, and then SON and DJF in the northern hemisphere. And then for the large region of mid-latitude and tropic is actually well simulated. The cold temperature, we're going to dive into that, and then we hypothesizing it's related to sea ice fraction and snow thermal conductivity, but we will look into that in details. What about global precipitations? So the bottom figure shows you the zonal mean precipitation global figure. Luckily, we don't have this double ITCZ problem that are usually very common to many of the global models. However, when we look at the global pattern, you can see we have this underestimated for the precipitation in the tropical land region, Amazon, West Africa, Indonesia. But for the subtropic Indian Ocean, you see there's a large precipitation overestimation. We can also look into the seasonality, where you see that this seasonality precipitation bias pattern also shifts by season. So in the JJA and SON, that the precipitation are mostly overestimated in the subtropic Indian Ocean, and then the DJF underestimation is very obvious in tropical land region. Try to remember, this is convection, parameterized convection, 60-kilometer resolution. We can take a closer look into the US. What are we doing in the regional temperature? There are two obvious patterns. This wind cold temperature biases, about 2 to 3 degrees cold temperature winter biases are associated with sea ice thickness and snow thermal conductivity. We'll look into that in later. And then this summer warm temperature in the central US, about 2 to 3 degrees, are also correlated with the dry precipitation deficits. The same figure, but then for precipitation seasonal. You can see the obvious pattern is this underestimation of precipitation in the central US in summertime. So we understand are a lot of organized convection happening in the southern Great Plains and also in the southeast US, these are isolated convection. Remember, this is parameterized precipitation at 60 kilometers, so it has difficulty to resolving them. But if you look at the DJF precipitation in the central US or a big part of the US, it's looking really good. This is what we know, actually, the summer warm temperature biases and then the dry precipitation biases is something we know. It's a common problem for global models in this region. And then coming from the WRF community at high resolution and then the CONUS experiences tells us that it's not only a resolution problem, it's also a land surface model coupled with higher resolution. This is scale-dependent resolution problems. So just to give some of our previous examples that Mike's study with coupled groundwater that is really manifest this land surface or shallow groundwater interaction with soil moisture manifested at kilometer scale. On the right is what are these crop model and irrigation processes we've done with WRF and NoahMP that is increasing your resolution. And with this land surface process, it can increase your precipitation recycling process in the central US. So this also gives us some experiences. We know these are the known problems, and then we have potential solution for it. I really hope that we could have this groundwater processes and crop irrigation processes into MPAS as well. Next one, we're going to look at this winter cold temperature problems. How are they? So we've done some sensitivity tests. So one thing we look into is this sea ice thickness. So remember, sea ice fraction is prescribed from ERA5, but then the thickness is a hard-coded parameter sitting in MPAS code. We'll try to tune a little bit down to from 3 meter and then down to 1 meter. You can immediately see the warm temperature warmer, 2 to 3 degrees warmer in the northern part of the US as well as in the East Asia, Eastern Europe. Another parameter we try to play around is this snow thermal conductivity. So it's a parameter option in NoahMP name list that what it changed is how the soil snow thermal conductivity is parameterized based on snow density. So number one give you growing of snow thermal conductivity with more dense snow. And then number three, just use a very high thermal conductivity all over, regardless of your snow density. So what it shows here is this, since the snow temperature or the 2 meter winter temperature are sensitive to snow parameterizations, that if you change to a high value of snow thermal conductivity all over, it will show you that the the temperature warmer in 2 to 3 degrees in the North America and as well as in Asia. But you will get warmer biases in Asia as well. So the idea is that these are some of the parameters, the cold temperature biases issue that we know. We've done some sensitivity tests. What are others global model perspectives? So these are winter storm track. We're looking to, with a very simple diagnostic, look into the daily mean sea level pressure variance, so how your day-to-day change of mean sea level pressure over time into DJF. So identifying it, there are two very obvious storm track, one in Pacific and one in Atlantic. They are all presented in MPAS, so those are good things. One is doing a little bit weaker in the Pacific, and the other one is doing a little bit stronger over the Atlantic Ocean. What else? We also look into the ENSO precipitation variabilities. Remember, this is SST-driven runs. So we are looking at the precipitation response to prescribing SST anomalies. These are the DJF precipitation for the strongest Nino years and then the strongest Nina years over the 25 years simulation period and their contrast. You can see that they're actually high correlation coefficient up to 0.8, and then their differences are about 0.71. So I think it's quite good for, well, not too bad, I mean, in the parameterized convection with prescribing SST. Next is tropical modes of variability. So I'm not a tropical wave expert, so I got this figure from credit to Kai. Kai helped me put this figure together with daily precipitation fields using GPMI merge and MPAS. What are these major modes of tropical variability are subseasonal predictability source. The good things is all these large-scale Kelvin wave, this one, and then Rossby waves, this equatorial Rossby wave, and then MJO is this yellow pattern here, and then the mixed Rossby and gravity wave are all presented in MPAS. Some are doing stronger, some are doing weaker. This Kelvin wave is a little bit too strong, and then MJO a little bit weaker. And also the faster 2000 mixed Rossby and gravity wave. So yeah, I'm not a tropical wave expert, but I will really infer this question to Kai. Also credit to Julia. Julia helped me put together this runtime integrated water vapor transport into the model. So you can look at this from runtime model output. I thought it's really cool to put this figure or animation here. What it shows is from the global 25-year run. It's one of the season DJF that you can really look at this high plume of purple IVT hitting the US West Coast. So those are atmospheric rivers. We haven't really looked into detail how are these IVT tracking or water vapor tracer doing with the atmosphere river, but the model has this capability to do so. So this is the first part of my presentation, that what are the long-term simulation give you the global temperature, global precipitation outlook, that for spring, summer, and fall, the temperature looks okay, the biases. And then winter temperatures, we know there's a cold temperature biases related to sea ice thickness and snow thermal conductivity. Global precipitation right now is parameterized at global 60 kilometers, while the response to ENSO are well captured. Summer dry precipitation deficit and warm temperature biases is a well-known problem. And then winter storm track, tropical rainfall wave mode, and then the capability to resolve atmosphere river over DJF. So these are the first part of my talk. And then the second part, we'll look into what are the land atmosphere coupling perspective, how are the model doing in the 25-year long run. The first thing we look in is this snow problem. So snow cover fraction, we are evaluating the model's snow fields against the modest snow. So you can see that the mode is showing on the top and then MPAS-NoahMP on the bottom and their differences on the right. I also correlate them well together with the DJF temperature. What are you seeing here are the three boxes I selected from North America, Central Asia, and also Europe. What it shows here is cold temperature biases in blue color are usually associated with over snowpack regions. And then the higher of a snow cover fraction, the colder temperature you got. Those are the correlation we identify. The cold temperature potentially lead to snow problem. What else? The second part, we'll look into soil moisture differences. So we do this evaluation against SMAP satellite. So SMAP was available after 2015, and then we'll look into the daily soil moisture fields. So on top, you're seeing the soil moisture mean value, and then at the bottom, you're seeing the standard deviation of the soil moisture. What you see here is obviously that the model for the mean soil moisture, surface layer soil moisture model is overestimated. But what's the biggest difference is if you look at the standard deviation of the first layer soil moisture, the model is NoahMP, it's doing underestimating its standard variability. So basically, the satellite gives you more variable soil moisture, but then the model underestimated. We look into speculate a little bit, and then it's possible due to the soil organic matter. What NoahMP does right now is that we don't really parameterize this soil organic matter, and then that would change the soil hydraulic product texture in the high-latitude soil. So basically involving that you have much less variable daily variability of soil moisture for the first layer in the high latitude. This where soil organic matter are really condensed. The next one, we look into the daily latent heat flux fields against these GLEAM products. So GLEAM is a model product, and it has some machine learning in it, but it's a daily product that we can look into that has a long record. So the GLEAM soil moisture actually show you on the top for the mean value and then the standard deviation at the bottom. What it shows here is, remember, we have a soil moisture overestimation, but the standard deviation is much smaller. But what it shows here is it still keep this overestimation of latent heat fluxes, but then the standard deviation of the latent heat fluxes is overestimated. And then the bias pattern, if you look into the right-hand high figure, and for the JJA months, that some of the underestimate of latent heat fluxes over Amazon or the land Africa, central tropical Africa regions are potentially related to the precipitation field that's underestimated precipitation from these two regions as well. And lastly, for the land atmosphere interaction perspective is that we can look into the coupling indexes. So I already showed you the first two panels. The first two rows are for the standard deviation of latent heat fluxes, and then the standard deviation of soil moisture. So those are, we compare data from three sources. regards of the FluxNet data from the left, the middle column shows you ERA5, and then the right column shows you how the MPAS and NoahMP doing. So I want you to focus on actually the bottom panel. It's the product of this standard deviation of latent heat fluxes, and then the times its correlation between soil moisture and latent heat fluxes. What it shows here is that the bluish color means it's positively coupling, and then the orange color means it's negatively coupling. Many of the land atmosphere coupling hotspots are identified over ERA5 as well as in the NoahMP MPAS. You can see, for example, this positively coupling in the blue and blue color is centered in the central US, in particular, Indian subcontinent, as well as in the Sahel Africa, northern China plain. So these regions are positively coupling, and we usually call them land atmosphere coupling hotspots. So the model is capturing the spatially, climatologically okay. So these parts summarize what the land model do. So trying to give an overview of all this land atmosphere coupling processes, what can do. That's we're looking into the snow cover fraction with overestimating snow cover fraction leading to cold temperature biases. Soil moisture, it has wetter soil moisture, but lower variability at high latitude, which could be missing soil organic matters. Latent heat flux at high latitude actually looks okay, but then mid latitude is overestimated. The tropical is underestimated, possibly due to this low precipitation biases. And the land atmosphere coupling strength is capturing this land atmosphere coupling hotspots globally. With this FluxNet data are too coarse or too sparse, and then ERA5 data. We are also actively looking into satellite products, so this will be contributing to our further analysis in the future. So this concludes about the long-term simulation part, where we look into the global climatology of the model performance, temperature, precipitation, and then the land atmosphere coupling perspective. I want to switch to the second part of this talk, is that since we already built these long-term simulations, we can use it and then to run a subseasonal forecast on some of the extreme events. So we look into 3 different extreme events. The first one is in 2021, the February cold air outbreak in the central US. This cold air outbreak, on here I'm showing the map of cold air temperature from ERA5. You can see the large blue color showing the entire central US is very, very cold, -10 degree of cold anomalies. It's not only cold, but it also caused power outage. So this is the Houston city before the storm February 7 and after storm February 6. That's not only too cold, but also power outages. It's a huge disastrous events. The next one we look into is the Pacific Northwest, the heat wave. This happens in the same year. It has to cross the US and Canada border. It's not only very warm, too hot, but also it lead to this wildfire in Lytton over the Canada side. And also remember, in Canada or Pacific Northwest, in particular Canada, people don't have AC in their homes. So what are these really devastating events? The third one we are looking into is this Texas flood in 2015. It's in contrast to the 2 events before. This is not only 1 week event, it is a 4 week of anomalous heavy rainfall. What happened is that year is before this extreme precipitation, Texas has experienced a long-term 5-year drought. But then after this flood, it's changing the hydrological regime from a dry region to a wet regime. So try to frame it as a very state-changing event. So how are we setting up our model? This is the MPAS S2S suite is a huge thanks to Abby. So Abby has built this S2S suite looking into I'm trying to use this example to illustrate what Abby has built up this S2S suite. So we are initializing, for this event, we're initializing every Monday, initializing reforecast with 11 members, 10 members from the ERA5 ensembles, and 1 member from ERA5 reanalysis. The same SST and sea ice fractions are prescribed from ERA5, and then the land conditions are substituted from an offline NoahMP run driven by ERA5. So for example, you see, for example, this cold air outbreak happens between week 4 and week 5. And then these are the 4 initial conditions before the event, and then for each of the 4 Monday before this event, and then we call them actually day 4 to day 10, corresponding to your week 1 forecast, day 11 to 17 to week 2, and etc. Right now, Abby has already finished a 5-year run from 2015 to 2021, and we will need to finish all the 20-plus year reforecast starting from 1999. Verification is calculated based on this removing a long-term climatology, which was I was showing from the last part of the presentation, and then by removing a 30 days moving average. So it's done by both ERA5 and MPAS-NoahMP, so you're looking at the anomaly field. So how does model capturing this cold air outbreak event from weeks before? I'm showing here is the anomalies temperature. On the left is the ERA5, and then on the middle is showing you the full initialized forecast and then the ensemble mean of the temperature outbreak. You can see that for the week 1, it's still in the deterministic forecast range that can give you a very good spatial and then the magnitude of the cold air outbreak. And when you transition to week 2, the spatial pattern is there, but then less of much of the magnitude. In week 3, the cold air outbreak is still there for much of the northern latitude, but they're not as strong as in the southern part of the analysis domain. And then week 4, when you go to day 25 to 32, the ensemble mean will give you a warm anomaly. Those are the ensemble means, but if we want to look at the ensemble spread, that tells you more of the information. So for the first week, it is in the deterministic forecast range. The model doesn't actually show you a quite big of a ensemble spread. However, when you transition to week 2, the ensemble spreads are actually quite large, and some members are doing really good compared to other members. And then week 3 and then week 4. So even though week 4, the ensemble mean give you a positive or close to 0 anomaly, but some members still capturing this negative 10 degrees of cold anomalies. How does this initialized forecast comparing if we try to calculate it based on ask a question, how many members would exceed the climatology 90 percentile, and then we call it extreme. What are these probability of extreme events? We look into these 4 initialized forecasts. Starting from January 18, it gives you 9%, January 25, 27%, and then February 1st, 54, and lastly, when you start this February 8 initialized forecast, it's 100%. How does it compare MPAS performance with operational forecast? So I look into the literature. So there has been literature looking to ECMWF and then the NSF, that's a CFS V2 operational model, calculating the same metric, how many members would just exceed a 90 percentile climatology. So this is what the MPAS these S2S extreme event trying to give you, comparing to operational forecast. However, on the right side, I want to note, because NSF and ECMWF, they are operational forecasts, they use coupled ocean. But MPAS-NoahMP is a reforecast, so we're taking most from the reanalysis and then prescribing SST. So what it does say here is not, it's doing better than the operation, but it's with the prescribing SST and initialized field. Those are the performance you could expect from weeks ahead of this cold extreme event. So this is the first event we try to look at. The second one, we want to look into the Pacific Northwest. The Pacific Northwest, we do the similar analysis, but focusing on the Pacific Northwest domain. And then looking to the same 3 weeks initialized forecast and look into their ensemble mean. The first week, or day 4 to day 10 give you a quite good of a warm anomaly over the Pacific Northwest. And then into week 2, that the ensemble mean has less of the magnitude, but the location is very good. And then transition to week 3, you will see that the ensemble mean give you basically 0 anomaly, so close to 0. What are the ensemble spread going to tell you is that you can see still the week 1 ensemble spread not very big, but then it gives you a quite good of a forecast in compared to ERA5 anomalies. And then into week 2, some members are doing really good compared to other members, which has given you a not very big of an ensemble mean. But then the ensemble mean, the magnitude is there, but then some member doing better. Week 3 is still the same. The ensemble mean give you close to 0, but some member doing better than other members. We calculated the same matrix. How many members will exceed climatology 90 percentiles? And then the statistic are showing on the left. And how does MPAS model compare with other S2S models? It's also looking to some literatures. So this literature comes from S2S prediction projects where people have put together a collaboration with multiple modeling, S2S modeling centers. So here are evaluating the 10 modeling centers from global centers. And then we're looking to the forecast week, initialized forecast week 1, week 2, and week 3 anomalies. So usually the week 1 anomaly sits between, other models are doing between 4 to 9. And then MPAS-NoahMP are about 7. The second one is week 2 that most of the models are sit between -1 to 4 degrees. And that MPAS is doing on the upper limit of this warm anomaly. And then transition to week 3, all other models are showing close to 0 or 1 degree of anomaly. And then MPAS is also doing just 1 degree of anomaly. So this is just tell us, we can also say that this is how to this one, the S2S models are actually comparable because these are reforecast. Some of them are reforecast. Some are with coupled ocean, some are with prescribed ocean. Okay, these are the second event we try to look into. The third one is this Texas flood event. So remember, this is not a 1 week of event. It's a continuous 4 week of extreme events. So here I'm showing the time series of weekly anomalies of precipitation in the Texas, Oklahoma region. These are the 4 weeks we're going to look into. This is, you can see that from the observation, precipitation observation, you can see that above about 300 millimeter for these 4 entire weeks of precipitation over the Texas and Oklahoma region. After this extreme precipitation, you will see that more than 90% of the reservoir are full, according to Texas Water Development Board. So I think in response to, related to this water resources management perspective, how are people can utilize this important information if they know the events are coming in weeks ahead. And after this, a period of anomalous and consistent precipitation, in the middle of June, there's another wave of tropical storm Bill that's built around another heavy rainfall in middle June. So these events make a consequence and also adding to this already very wet and then precipitation into Texas. How are the model doing? I'm trying to show you here is the conjunction of this 4 week, and then we are going to look into the week 1 forecast, week 2 forecast, week 3 forecast anomaly based on the conjunction of these 4 weeks. So what it shows here is the week 1 forecast anomaly of lead time, week 1, so this day 0 to day 6. You can see that the pattern is there, and the location and anomaly is there, but not as big as what it shows on the observation. When it transitions to week 2, you will see that the week 2 forecast anomalies are much less. The pattern is there, but the persistence is there, but then the magnitude is much more smaller. Also, the week 3 forecast for this 4-week period is that it's still showing you about 80 millimeter of the positive anomalies over these 4 weeks of period, but then the anomaly magnitude is much smaller from the ensemble's mean. That's what we try to put it here. If you only evaluate your subseasonal forecast based on ensemble mean, that's the information you're going to look. However, what's really important is to look into ensemble spread. I'm going to show you this. This is the time series I already shown before, and then benchmarking it with 90 percentile and 95 percentile from the observational records. How are the model doing with week 1 forecast? This is the week 1 forecast with the blue lines. So this is a parameterized 60 kilometer resolution. Week 1 actually exhibit high fidelity of the ensemble mean. Some week are missing, some week are doing really good. Especially you will see that the 2nd week, 3rd week, and then the last week of this extreme event period. And then afterwards, this tropical storm is actually doing okay. How about week 2? Week 2, so if you only look at the lines are showing you the ensemble mean. However, the ensemble spreads from week 2 are actually giving you more information comparing to only the ensemble spread. So it gives you the magnitude of the ensemble mean is smaller, but then some models are doing better than other models. Some members are doing better than other members with the week 2 ensemble spread. How about week 3? Week 3 is that if you only look at this 4 weeks period, ensemble spread of week 3 precipitation can still provide you information. In particular, for example, we look at this week 3. The week 3 precipitation, the 3 dots give you 3 weeks of ahead that your precipitation 3 weeks later will be more than 90 percentile above climatology. So I think what it sits here is that it deserves to look into the interpretation and the communication of how the S2S forecast is very important. There are certainly different things to look into at different lead times. Perhaps in week 3, there will be a strategic watch. When you want to look into the large ensemble spread exceeding the extreme threshold, that actually flags you a specific time and region for increased scrutiny. At week 2, this will be a heightened awareness, the persistency and then the clear timing of the signals that warrants actions. And when you get to week 1, that's the operational actions. This high confidence of forecast provides you certainty that needed for concrete actions. So this is something that we hope to convey that when you only look at the ensemble mean of the week 2 and week 3 forecast, you're not getting as good as that in your week 1, but then the ensemble spread can tell you more. This is kind of the summary slides for these 3 extreme events. So MPAS is doing okay for the global 60 kilometer with this winter cold air outbreak. You can doing better than the summer heat wave. And then the ensemble precipitation spread for the Texas and Oklahoma extreme flooding or extreme rainfall, those are the important information we will try to convey in terms of the probability of extreme is important. And then we right now have 6 years reforecast, and we'll need to evaluate the 20+ year reforecast when it will be available. So after all, this is my key messages. We hope to document MPAS-NoahMP performance, both in the 25-year long-term simulation as well as in the S2S forecast. And then it will be evaluated over this 20+ year reforecast once it's finished. We identify some problems and then potential room for solutions. Those snow thermal conductivity and sea ice thickness for winter cold air biases, and then some of the land surface features for groundwater, crop growth, irrigation for summer warm, dry biases. And the third one is really emphasizing this is a collaborative effort across labs to advance this process level understanding of both land atmosphere interaction and S2S predictability. Those are major part of this presentation, and I also want to highlight what are the next steps. So right now, what we are doing is global 60 kilometers, but then in the future, we want to do regional refinements. And this is the effort between this cross-lab group. So Meg and I and Abby, we put together this NSC proposal to do this regional refinement for S2S reforecast. And then MPAS, so CSM is doing 100 kilometer to 15 kilometers, and MPAS has two domains. Global 60 kilometer to 15 kilometers, and then global 60 kilometer to 4 kilometers going down to convection permitting. We have the shared science goals that evaluating this impact of grid spacing on S2S predictabilities, and then in particular look into these extreme events, and then the land atmosphere interaction focusing on soil moisture and precipitation feedback. What are other ongoing, this is the SPAD S2S working group. Really great thanks to Meg. Meg has been organizing this working group, SPAD working groups. So she's the community liaison for our groups. Right now we have a few, 5 groups, and then the matrix groups has 2 parts. So there's a process-oriented matrix group and some of the application-oriented. For some of the application-oriented group, you can think of what are the application of your research focus, and can you derive it from an atmosphere model? If you can derive it from an atmosphere model and then fit into your application purposes, how are these matrix looking back 2 week, 3 week, 4 weeks in a lead time? The regional refinement simulation, I already introduced that, and then with that, an SC proposal has already been approved. So we will try to conduct that simulation in the coming months. For myself, I'm personally interested in agricultural, so look into how agricultural outlook can go into have the next 45 days outlook for agricultural growth. Extreme events, those are what it show apart from what I have presented the last few slides, the extreme event case studies, and then also trying to do coordinated experiments between different labs and also different agencies between NOAA, NASA, and DOE. So last but not the least, we right now, there's Chenling, Sanjeev, Alexi, and Meg has put together this AGU cross-journal special issue. So the topic will be about subseasonal-to-seasonal predictability and extremes, role of land atmosphere. We really hope, if this topic you are interested in, and hope to see your contribution. And thank you so much.
Thank you for that great presentation. It's great to see all these efforts that you're going on, and I'm sure it'll inspire a lot of questions. I want to mention for people online, do feel free to enter your question on the Slido, and we'll take questions from both venues. Let's start with Mike.
Okay. Yes, great talk. Thank you very much. I'm curious, with the NoahMP in your runs, did you have the dynamic vegetation turned on? No, so it was static based on the climatology? Okay, all right. Well, that may be another area to squeeze some more predictability. So yeah, okay, thank you.
Yes, thank you. So I think along the line, so dynamic vegetation is a big part, and then so coming back to the warm temperature biases and the summer precipitation biases. Yes, this figure. On the bottom is that if we have a coupled land surface model with this groundwater, crop, and irrigation, and then down into kilometer scales, can we really resolve this precipitation, soil moisture precipitation feedback at convection permitting scale, and then improve not only your predictability, but also the model climatology in summertime? Thank you so much.
Sorry to jump ahead of people, but I did have a related question to this. Is it possible that it's missing some tropical cyclone activity as well?
Great question. So I want to show you the seasonal figure. Yes. So the U.S. Southeast, so to be honest, I'm not a tropical hurricane person. And then I'm not quite sure, does global 60 kilometer can resolve hurricane and also hurricane-related precipitation? So those are the challenging field. But hopefully, if we get to the regional refined simulation, and one of the domain is global 60 to 15 kilometer, that potentially can give you that answer.
Thanks. We do have a couple questions online too, so I'll go to Andy Wood. He mentions nice talk. I'm curious whether you plan to re-estimate the week 1 to 3 anomalies based on the climatology from the hindcast at each lead time when those are done. That would exclude any bias tendencies in the forecast system, which may have a climatological drift by lead time.
Yes, yes. Thanks, Andy. I think this is actually the proper way to do so. So for many of the S2S run, those are, I think Judith and Abby are trying to do this. It's called lead time dependent biases. And then right now we are only removing the long-term climatology biases, which is not the same. But once this 20 years reforecast is finished, we are able to reassess the week 1 to week 3 process biases, anomalies based on these lead time dependent biases.
Okay.
Ask Falco's question and then I can follow up.
No problem. Yeah, we'll go to Falco Jute. Okay, I have 2 questions. How do the probabilities from the S2S MPAS ensemble for the extreme events compare to climatology? Is the ensemble skillful in the sense that it gives you a higher probability than climatology? And 2, have you looked into false alarms?
Yeah, thanks, Falco. I also want to say thank you to Falco because many of the initial script that Falco shared with me to do the remapping, so really thanks. In terms of the predictability ensemble spread, how does it compare to climatology? So this is showing the climatology of 90 percentile cold air, and then it's not the model climatology, it's the observed ERA5 climatology. So it actually tells you the model capability ensemble spread to not predict model extreme, but try to predict observed extremes. So I think that's give you more credibility compared to your predicting a model extreme. And then the second question is false alarm. Okay, that's really good question. And then that's better examined in the precipitation case. So, okay, look into this false alarm. You can opt for this summer season, you can already see some of the false alarm. For example, your April 20 case, where your week 2 and week 3 give you a very large ensemble spread, but your week 1 is low, and then it's below anomaly. So that's kind of the false alarm. But then the message is trying to go from here is you can look into it in 2 ways. That's what I would say for week 3 and week 2 is more of a strategic watch and then a heightened awareness. But then as time progressing into week 1, that gets you better confidence to act. But there's certain trade-off here. If you try to prepare in a longer lead time, that give you a long time to act. But if you try to wait longer for a shorter lead time, that give you a shorter time to respond. So kind of a psychological trade-off here.
So one thing kind of to follow up on Falco's question is once you have your reforecast, or never mind the whole reforecast, once you would have just a series of extreme events simulated, I think what you urgently need to do is you need to compute the area under the rock curve. So the receiver operating characteristic. So that's going to define this critical metric of forecast skill, and it's essentially whether the forecasts are useful or not. So that will let you go away from these sort of squishy qualitative definitions of like, well, we think they're good for like, watch and warning. You maybe start thinking about planning. No, it actually will give you a quantitative metric as to, okay, you have useful skill out to such and such time scale. That's one. Second is when you're looking at all of these events, you're looking at the end products of precipitation and temperature. Have you looked at like the atmospheric circulation anomalies themselves? So like for the Canadian heat wave, that was a highly, highly anomalous ridge over Western Canada that had some tie to like large scale dynamical forcing. So are you getting those things right in the model? So you have to, I think for each of these events, it's not just that you're getting the end result of the precipitation or the temperature forecast. It is, are you getting the the dynamics and the sequencing of things right?
Yes, wonderful question, Chris. So to the first question, I think we will be doing that. It's a good suggestion to look into the ROC curve. And then for your second question, large-scale dynamic field, actually I prepared some figure for, if we just look into the Canadian heat wave, Pacific Northwest heat wave.
Yep.
Okay, so what it shows here is why does some member doing better member than other members? And then we can tease out these three initialized forecasts and look into the good members and bad members. And what we try to predict is on the left, is top left, is ERA5, Z500 fields. Some of the good members, you can see that week one and some of the bad member and good members are not very distinguishable because these are very close, still very close to your initialized. But then when you're progressing into week two and week three, what's really making this member goods are the ability to get this ridge pattern over Pacific Northwest.
Right.
So I think those are some of the things, trying to explain it why like some members are doing better than other members.
Okay, I'm sad to say we are running low on time, but we do have one last question online that I'll get to by Li-Feng Lu, who compliments your talk and says, maybe I missed it, but can you clarify how SST was prescribed in the reforecast, and is it fixed in the initial time or evolving as an ERA? What is the plan for SST in the reforecast experiment?
Yes, thank you very much. So that question actually is a similar treatment as in the WRF. So WRF used SST as a lower boundary condition, and then we update it every daily from ERA5. So it's a daily updated time varying SST field. And then for the reforecast, we are trying to do it the same way. So using a daily updated SST from ERA5.
Cool. So I just want to ask really quick as we end this talk, are your data sets, they seem like they'd be really useful to the community. Will they be available to the community for collaboration with you guys? Or?
I think, yes, the 25-year-long simulation is sitting on campaign. So yes, of course. And then the S2S reforecast right now, we only finished part of it, but once it's finished, yeah.
All right. Well, thank you very much for covering this great talk and our materials. And everyone knows where to find Jer, so please do stay after to talk or meet him afterward to discuss this great research. Let's give him one more round of applause.